Today, I'd like to talk about the heap as a data structures. In particular, I'd like to talk about the min and max heap. And a min heap is a data structure which guarantees that the first element is always the smallest, and the max heap guarantees that the first element is always the largest element in the heap. And now, where is this useful? It is very useful for having a priority queue as in you can queue up different tasks, and then you can just ask the queue to give you the first task, which is, for example, the most important or the least important task, depending on if you use a min or max heap. And the removal is in itself O of one, which is constant time because you just remove the first element, but this would disrupt the heap property, so you have to heapify it from the top to the bottom, which is a log n operation. So since it's constant time, it is a constant. So essentially what you can think of a heap is you have your removal operation, which is um, O of one, right? O of one plus uh, O of log uh, Q n, and where n is the number of elements you are currently storing in your heap. And because we have we when we use big O notation, we do not count the constants. We just say it is O log Qn of time complexity to remove and regain the properties of a heap, right? Just removing is all of one, but if you just remove it, you can do it only once. But now let's move on with the heap. Just for a better representation, let's open Wikipedia and look at what a heap looks like. Wikipedia heap, right? Uh, right? Data structure, and we can represent a heap in two different ways. We can have it as a tree or as an array, and I'm using the array representation. This is just because an array representation has better cache locality because we have a contiguous amount of memory, which means all elements are in a row essentially. Whereas when we would use a tree, we'd have memory fragmentation, which is not good for cache locality. And mm, essentially, this is how a heap can be implemented. And here we can look at the different operation. And the big O notation comes to the same conclusion, log n, which is not actually really true because if you think about this, we implement a binary tree, and the binary tree divides all the elements ideally at every node by half. So we if we choose to go left, we should be reducing the amount of nodes we have to search by a half, and so on and so on. So to be precisely mathematically correct, it would be O of log a n, right? Where a is the amount of subtrees each node can have, right? So in our case, a is just 2, but if we had a is equal to 4, we would get even faster search speeds at the cost of losing this property, which is that we can use this where is it? This formula to compute the indices in an array, which is, in my opinion, worth more than getting this marginal better optimization. Because if we do log 2 of 1 is 13, right? And if you do okay, it's twice as fast. So it is important, but you see, we still have like 10,000. Let's do it 1, 2, 3, right? And 2. It's still only 13 comparisons, 23 to 13 comparisons, so it should be, it shouldn't make any difference in our case. And as I said, cache locality is everything. But now let's look at the implementation itself. We have a non-generic, we have a generic implementation for creating a heap and for creating with the capacity to minimize memory allocation. So if you know how many elements your heap is going to hold, then just use this function because this is way more efficient than the function above. Then we have a length, which just returns the length of the underlying vector. Then we have a non-generic function, which is restricted to the min heap. The min heap itself is very simple. We have a function that pushes onto our vector, and if we have more than one element, so if the value we're adding is the second or third or whatever, then we can call the heapify method, heapify heapify swim as in we go from the bottom bottom of the heap up to the top to the root. This is why swim. We essentially surface, and this is implemented in this case, and we just take the last valid index is the current node, and its parent is it's the current index minus 1 divided by 2, essentially just the inverse function of this formula here. So we can derive it from looking at this formula. We can derive this formula, and then what we do is we compare the current node to its parent node. And as it stands now, we only have to go like one direction of a subtree because we already guarantee by doing it every time when we add a new element that every parent is the smallest of all subtrees, right? So this is why we only have to compare one way, which is why it gets the log n time complexity and not an n time complexity. Yeah. And then once we reach either a case where we don't have to swap, then we know it's sorted because we do it at every iteration, meaning every subsequent iterations are already sorted, and we know it because we call it every time. Or we reach the case where we have reached the parent node, meaning that our current node is, for example, now the smallest or the largest node in our heap, which is what exactly a heap is and follows its definition. So this is also fine, and then we just break out of the loop. And this is how we can go from the bottom up to the top. And adding in itself is really simple. We just do a swap remove. This is where we have to be a bit creative because we're using a vector, right? A vector is represented as a contiguous amount of memory, such that if we remove the first element, we would have to either shift all the subsequent elements by 1, which is n time complexity, right? And then we would also preserve the structure if we were to just shift all by one element to the left. This would also work, but we can be very smart about it. We can say, okay, we just take the last element and the first element and just swap them around, right? So that we can just pop the last element, which was previously the first element, from the vector without moving the rest of the element, which is O of 1, which is constant time. It always takes the same amount of time, no matter the input size. And then what you're going to do is you're going to say, okay, let's think about it as subtrees, and let's compare each subtree to each other. And by using like a mental model of a tree, we can subdivide every node. We can subdivide the amount of nodes we need to compare by 2 at every step we take. So in every iteration, we essentially divide the amount of work we need to do. And the idea here is that we just look at 3 nodes at a time, essentially a parent node, a left child, and a right child, right? That's the base case. And then we look at at the first case where we have the case that L, the left child, is smaller than the parent node. So we just switch it around. And then we go down the left subtree, which is the parent node, and so on, so on. And we do this recursively, or in our case, iteratively, with an in-place loop. Our next case could be we have a right subtree whose parent node R is smaller than the root node P, and then we do the same thing as we did in the case of the left subtree, just in the other direction, in the right direction. And the most tricky case is when we have case A and case B at the same time, meaning we see first, okay, L is smaller than P, but L is also smaller than R, meaning R is smaller than L and L is smaller than P, which should give us this tree. And then we just go down the right subtree. Again, because why does it work? Because we guarantee with the insertion that every tree level, that all nodes in tree level, for example, if we have tree level 1, which is the root, then we have 2, then we have 3 tree levels, right? That every node in tree level 2 is larger or smaller depending on if we're using a max or min tree than at the tree level below it, right? So we know we only have to look at those and know that the rest should be good. Okay, but now let's look at Heapify Sync. This is a function way more complicated than the first one, as we can see, just by the size of it. The first thing we do is we take a parent index, which is in our case just 0, the first element. Then we compute with this formula derived above its left and right child. Once we have that, we try to get its left and right child. And if it has neither a left nor a right child, we say, okay, it is the leaf node, meaning it is either the smallest or the largest, so we just break out of the loop. If it has just a left child, we just say, okay, is the left child smaller than the parent or larger than the parent child? If it is, depending on which heap we are implementing, we just switch them around and say, okay, now the parent is set to the left child, meaning we compare the left child subtrees to each other in the same manner here. This is where it begins. This line here is where the recursion is, because instead of recalling this function, we just use a loop with new values. The same goes for the right here. And as I said, a case C is the most difficult cases of all. We have the case where we have a left and a right child. So what we do is we encode state in those two variables here. We have an option bool and an option bool for go left and the union. So basically, did both cases occur? This is what I meant with the union AB, right? And first we check the left, and if the left has, if the case A has happened, it means that the first condition for the union is valid. So we set it to some false, and we know, okay, no matter what, we need to go the left subtree, right? We have to explore a left subtree. If this is the only case, if case A only happens, then we need to explore the left subtree. And to verify that, we check the right subtree. And if the right subtree is also smaller than its parent, then we have to say, okay, if we have to go left, then we need to compare it to its right subtree, the left and the right. And if the left and the right, if right is smaller than left, then we have this case C, which is denoted as sum true. Otherwise, we just say, okay, we don't go left anymore, we just go right, which is a sum false. And if we have a sum false, right, then we just go case B. We have to go down the right subtree by swapping the swapping the nodes in beforehand. Otherwise, we have to check if we have the case C, which is done here. If we don't have case C, then we just have case A and we go down the left subtree. In any other constellation, it means we didn't have case A or case B, meaning we just know for a fact that it is already ordered, and then we just break out of the loop. And this is pretty much how a heap works. I have some test cases here. We have insertion and removal. And from the looks of it, it appears to be working quite well. We can even take a look at it. Heaps, we have even debug print statements here. The heap structure is 13856, and when we remove it, remember, when we remove, we switch beforehand the 6 with the 1, so we have 63581, then we remove the 1, and then we have to restructure it. And this shows that the restructuring logic in this case works flawlessly. So yeah, I hope you learned something interesting today. In my opinion, I think heaps are very interesting data structure to implement, but I do not quite like them because they're very tedious to implement, and yeah, but that's pretty nice. And by the looks of it, just by looks of how much it is used, like we have binary trees, we have skewed, we have leftist, we have binomial trees, we have different kinds of heaps. Um, I think it's safe to assume that um, heaps are widely used data structures. And just looking at the different programming languages that implement them, we have quite a few implementations already, and even Rust supposedly has one. Yeah, even Rust has one. Actually, let's implement the clear method the same way Rust has one. This is why. Let's do it. Where do we go? Pub fn clear self. We just cleared, right? And how do we clear it? We do self dot data dot. So it's simple as that. And now we have cleared it. So yes, now we even have a clear structure, and we have the same. Yeah, we have the same pop push, right? Yeah, we have the same functionality even as the Rust data structure. Yeah. Anyhow, I hope you had fun. That's it for me today.